Hello everyone, my name is Anna-Lena and I'm really excited to be with all of you today. I want to use the next hour to take you on a magical journey through the world of Python, and I hope that you will enjoy it as much as I did when preparing this presentation. A few words about me. I'm currently working as a machine learning engineer in a great German company called Innovex, where I work on various projects surrounding data engineering and machine learning. In my free time, I'm working in a voluntary project called KI macht Schule, which translates into something like AI Goes School, where we teach kids in German schools about AI and machine learning, both online and usually also in the schools. I also like working on personal projects and usually share those with the community either on GitHub or my personal webpage. The two most popular repositories you might find interesting are Machine Learning Basics, which implements fundamental machine learning algorithms in plain Python, and My Magical Universe, which is the basis of today's talk. Every good talk needs a story. Today's presentation is based on a magical universe I created called the Tales of Castle Kilmere. I want to present the main stories and characters to you such that we can work with them throughout this presentation. The goal of this presentation will be to create the world of Castle Kilmere using Python. The main character of our universe is called Lizzie Spinster. Lizzie is a quiet, clumsy girl of age 12 who is sticking her nose into books most of the time. Her best friend, Luke Barry, is living next door and has a completely different personality. He's usually full of energy and full of mischief, constantly trying to convince Lizzie to play tricks on other people. One day, Lizzie's parents decide to send her to Castle Kilmere, a well-known magical boarding school, with the hope that she will become more open-minded when being surrounded by many other children. But only after Luke's parents allow him to go too, Lizzie agrees. Castle Kilmere is a really old school which has been around for centuries. No one really knows how old the school is, but it's well known all around the world. The headmistress of Castle Kilmere is called Miranda Mirren. Although Miss Mirren is a very strict and stiff witch, she cares greatly about extracurricular activities, her favorite being the Club of City Walkers, which she has presided over since she joined the school. Castle Kilmere is divided into different faculties, each focused on a certain subject. Naturally, all students have to take certain mandatory courses like critical thinking or basics of spellcasting. However, they are free to choose courses from other faculties. Each faculty is supervised by a professor. For example, we have Bertie Brittle, a chubby, lovable old lady who's the head of the Department of Law, since of course also the magical world needs rules. On their first day at school, Lizzie and Luke quickly learn that not all kids at school are nice. Some kids and their families have actually been associated with an evil magical society called the Dark Army. The Dark Army is led by a particularly dark wizard called Master Odin. Not many people know how Master Odin looks like, but everyone knows his name. He has been pulling the strings behind the wheelings and dealings of the Dark Army for years. This gives us the main information we need for this presentation. We will start out with some simple Python features, progressing to advanced concepts in the end. So independent of whether you're a beginner or a professional, this presentation will hopefully contain some new knowledge for you. To get started with our universe, we first have to talk about classes. Using classes in coding is tightly coupled to the concept of object-oriented programming. In this concept, programs are designed by creating objects that interact with each other, and where each object can contain attributes and methods. Object-oriented programming can be used to represent the structure of the real world. If you think about it, we have lots of classes and instances of these classes. For example, we have the class person and lots of individual persons like you and me who are instances of the person class. So what is a class? A class acts as a blueprint for an object. It describes how objects, so-called members of a class, are structured and which attributes and methods they have. The syntax for creating an empty class is quite simple. We start our universe with the class Castle Kilmere member. Our class currently doesn't contain any code, so we use the keyword pass as a placeholder in the body. Pass can be used to denote places where we will eventually put code. Right now, it allows us to run this code without getting an error. To actually create an object that is an instance of the class, we need to instantiate the class. This is also simple, as can be seen here. So far, our Castle Kilmere member class is boring and not very useful. We need to add some attributes and methods to it to make it more interesting. Each Castle Kilmere member will have a name, a birth year, and we know whether the member is male or female. This information is included in the dunder init method. If you don't know what the word dunder, this stands for double underscore and is typically used when talking about methods that start and end with 2 underscores. The dunder init method is called under the hood whenever you create a new instance of the class. So when creating a new member of the class, for example, our headmistress Miranda Mirren, the dunder init method is called automatically with Miranda's name, her birth year, and her sex. We can create the Miranda instance similar to before. So we call the class with the name, the birth year, and the sex. The dunder init method is now called automatically with these attributes and returns an instance of the class, which is then assigned to a variable called Miranda. Note that the first argument of the init method is called self. It points towards an instance of the class whenever the method is called. We also added a method called says, which adds behavior to our class. In this case, it allows our Castle Kilmere member to say something. So when calling Miranda.says, hello, my dear, Miranda will talk to us. These are notes about what I just said. The dunder init method is called under the hood when creating a new instance of the class. As mentioned, its first argument is self, which points towards an instance of the class whenever the method is called. The Castle Kilmere member class is nice, but of course we want many other classes in our magical universe. For example, we want to create pupils, professors, ghosts, and so on. But all of these are members of Castle Kilmere, right? So to express this relationship, we can use inheritance. Inheritance allows us to create a new class that inherits all attributes and methods from the parent class. The resulting child class can override methods and attributes of the parent class, and it can add new functionality. Inheritance is great for reducing duplicated code and for showing the semantic relations between objects. Let's use the concept of inheritance to create a pupil class. This new class inherits from our Castle Kilmere member class. In the dunder init method of this new class, we use the method super to call the dunder init method of the parent class, which initializes the name, birth year, and sex. Then we add new attributes to the class, which will be specific to our pupils. For example, a pupil started school in a certain year, and they might own a pet. We added another attribute called elms, which stands for elementary level of magic. The elm attribute contains all the obligatory classes a pupil has to take. When creating a new pupil, she won't have passed any elms yet, but this might change once she writes her first exams. We can now create pupils, for example, our main character, Lizzie Spinster. For this, we call the class with the necessary arguments like Lizzie's name, her birth year, and so on. Let's sum up what we learned. Classes in Python implement the paradigm of object-oriented programming. They act as a blueprint for an object and describe what properties and behavior an object should have. We created the Castle Kilmere member class and used inheritance to create a child class pupil. The child class inherits all methods and attributes from the parent class, but can add new behavior and also override existing behavior. We further learned that inheritance is a good tool to show the semantic relationship between objects and to avoid duplicated code. However, you should be careful not to use too many layers of inheritance because it adds complexity and might make your code harder to read. Our magical universe now contains already Castle Kilmere members and pupils. With inheritance, we could also create classes like a professor and a ghost class. This concludes our first section. In this first section, we already created the classes Castle Kilmere, Pupil, and Professor and Ghost. In this section, I want to take a look at the different types of methods we can add to a class. A class can have 3 types of methods: instance methods, class methods, and static methods. Let's start with the most common one, instance methods. Instance methods are the most common type of method. They take at least the parameter self as an input, which points towards an instance of the class when the method is called. An instance method can modify object state using the self parameter and class state indirectly using the self.dunder class parameter. Our base class already has an instance method. The says method takes the input self and a string of words that the current member of Castle Kilmere should say. When the says method is called on an object, the self parameter can be used to access attributes which were set in the dunder init method, for example, self.name. The next type of method we will look at are class methods. Class methods look similar to instance methods in the sense that they take at least one parameter as an input. This parameter is, however, not self but CLS. CLS points towards the class, not a particular object instance when the method is called. Therefore, a class method can only modify class state but not object state. Still, changing the class state will affect all instances of the class. Another important thing to know about class methods is that we need to use the @classMethod decorator when implementing a class method. We will talk about decorators later on, so right now you only need to remember to put @classMethod on top of the function. We will see an example for a class method in a second. One important thing to note is that the names of the variables self and CLS are only conventions. It's best to follow them, but in theory you could give them different names too. Okay, so let's take a look at what class methods are good for. One nice way to use class method is as alternative constructors. You may now think, what is that supposed to mean? In a Python class, we can have only one constructor, namely the dunder init method we have seen already. But we can use class methods to write functions which allow us to create class objects that are configured exactly the way we want them. In this way, class methods act like additional constructors. For example, we probably want to create the main characters of our magical universe. Typing all the names and other attributes every time would be very slow. Adding a few class methods allows us to speed up the process. This example shows how to create a class method for Lizzie, our main character. With this class method, we can create the Lizzie instance very easily by just calling pupil.lizzie. The class method is decorated with the @classMethod decorator, uses an instance of the class to create the Lizzie Spinster instance. We could equally create class methods for other members like Luke Berry or our headmistress Miranda Mirren. The last type of method we will look at are static methods. Static methods take neither a self nor CLS parameter as an input. Therefore, they cannot modify object state or class state. Although they are related to a class, they are yet independent because they cannot access instance or class state, but only the data they are provided with. Let's look at an example. If you remember the pupil class, it had an attribute called ELMS, standing for Elementary Level of Magic. This attribute contains all the obligatory classes a pupil has to take. If a student passes one of her ELMS or not depends on the grade she gets. Castle Kilmere has a fixed grading scheme where grades range from E for excellent to H for horrible. This is perfect material for a static method. The static method we have here, called passed, gets a grade as an input and returns whether or not that grade means pass or fail. You can see here that the method uses no class or instance state, but only has access to the attributes it's provided with, which is the given grade in our case. We can call this method on different pupils. In this example, we first use our newly created class methods to create instances of Lizzie and Luke. We can then access our static method passed, both on the instances, on Lizzie and Luke, but also on the class itself. You might now wonder why we don't use normal methods for this. A clear advantage of using not only instance methods, but also class and static methods is that they allow a developer to communicate what intention she had in mind when implementing the method. For example, using a static method expresses that the method is independent from the rest of the class. We have also seen that class methods can be used as alternative constructors. This concludes our section on the different types of methods that can be used in a class. So to sum up, we have learned that classes can have three types of methods. The most common type of method are instance methods, but there are also class and static methods. You should note that using static methods is controversial. Some people advise against them, but personally I think that they can be useful in certain situations. Next, I want to talk about an extremely useful feature that came out with Python 3.5, type annotations. Type annotations are such a great tool that I use them every day to increase the quality of my code. Naturally, our magical universe should turn out to be great code too. And using type annotations will bring us closer to this goal. So what are type annotations? Type annotations allow us to add arbitrary metadata to function arguments in the return value of a function. Why is this useful? First of all, it allows us to document the types of our function parameters. Furthermore, type annotations can be used for things like type checking. There are more use cases for type annotations, but for our case, using them for documentation is already a good enough point to get started. The syntax is very easy. We just add a colon after each attribute and specify its type. For example, the variable name in our current constructor is a string, whereas the variable birth year is an integer. We can also specify the return value of a function. Our says function takes a string of words as an input and returns a string. This is expressed by the following syntax: an arrow followed by the type of the return value followed by a colon. We can also reference more complex return types, for example, classes. Our class method, school headmistress, returns an instance of the Castle Kilmere member class. This can be specified by using the name of the class as a type annotation for the return value. Okay, so we have seen now how to specify the return value. Let's continue with a bit more complicated type annotations. The pet attribute of our pupil class is given by a tuple which contains the name of the pet and its type. Both these attributes are strings. To specify that the pet attribute is a tuple, we first need the import statement from typing import tuple. Simple data types like string and integer can be used directly as type-ins, but this is not the case for types like tuple or list. After the import, we can specify how our tuple is structured using square brackets. So in our case, the pet tuple has two fields, which are both strings. An example for a pet is given below, where we have Ramses, Lizzie's large furry orange cat. Oh, there he is, sleeping as usual. This should give you a first idea of what type annotations are and how they are used. So to sum up, type annotations are a great tool to document the types of your attributes and return values. They are easy to use and make your code more readable. You should note that type annotations are not enforced. To do that, you will need a type checker like MyPy. Nevertheless, I would suggest that you start using type annotations if you don't use them yet. Our next section is about how we can convert objects to strings. Right now, our Castle Kilmere members cannot be printed nicely. For example, let's take a look at how the instance of Bromley, Castle Kilmere's loyal caretaker, looks like when printed. This is not very useful. We only see the name of the class and a number which represents the memory address of the instance. It would be much better to have a nice representation which gives the name of the instance and maybe some other useful information. There are actually two methods in Python that control how objects are converted to strings. These are dunder-wrapper and dunder-stir. Having two methods already points towards the fact that they must have different purposes, which is indeed the case. So let's start by looking what wrapper is for. The result of the dunder wrapper method should be as unambiguous as possible. It should function as a debugging aid for developers and should therefore be explicit about what the object is. If possible, dunder wrapper should return a representation of the instance that can be used to recreate it. What this means is nicely illustrated by looking at a datetime example. For those of you who don't know the datetime module, it can be used to manipulate dates and times, basically. In the example shown here, we import the datetime library and use its datetime.now method to compute today's date and time, and then we call wrapper on it. Take a second to think about how the object should look like to really get an unambiguous representation of the object. Here's the output. It tells us exactly what kind of object we are looking at and its values for the date and time. We can use this representation to recreate the original object by first calling wrapper on it and then evaluating the result. Let's take a look at stir and how it's different to wrapper. The output of the dunder stir function should be readable. Just think about how the object should look like for a user, not a developer. Going back to our datetime example, we can see that the output of stir of now gives a very different representation compared to wrapper of now. This output allows us to immediately see what date and time the object is representing. So the big question is, which of these two methods should we use? Many people recommend that whenever you create your own class, you should at least implement the dunder wrapper method. Why dunder wrapper? Because it will ensure a useful conversion of objects to strings. When Python looks for the dunder stir method, but stir hasn't been implemented, it will fall back to using dunder wrapper. So as long as dunder wrapper is defined, we will get a helpful representation of our object. Let's apply this knowledge and add a wrapper method to our Castle Kilmere member class. We implement our wrapper method to hold all important information, like the name of the class, the name of the instance, the birth year, and so on. This should give us a much nicer representation of our Bromley instance. So here you can see the old result we had before, and now you can see that we get a much better representation, which is much more useful. As you can further see here, our wrapper method allows us to recreate the Bromley instance from its string representation. As a quick summary for this topic, you should keep in mind the following two things. The first one is that we have two methods for converting objects to strings which serve different purposes. Second, try to add at least the dunder wrapper method to your classes to ensure that your objects have a nice representation when converted to strings. This concludes our section on toString conversion. The next topic I would like to cover is the Defaultdict class. The Defaultdict class is part of the Collections module. This is actually a really cool module, and I suggest you check out the other features it offers. For our magical universe, we will look at the Defaultdict class and how it's used. Let's say we want to extend the Castle Kilmere member class with an _traits attribute. So we add a new attribute to our dunder init method, which contains the character traits of a Castle Kilmere member. We further add a function called addTrait, which allows us to add attributes to a character, and a function which prints the character traits of an instance. We can now add traits to Bromley, the school's caretaker. Bromley is a very kind man who is tiny-minded. After all, he's a caretaker. But if there's something Bromley is not, it's impatient. We can now account for Bromley's personality by adding the different traits to the Bromley instance. We now want to add a function which checks if a Castle Kilmere member exhibits a certain character trait or not. As the type annotations show, the function should accept a trait as an input and return a Boolean, indicating whether the individual exhibits the trait in question or not. What we want for this function is to return false if a certain trait cannot be found. One way to solve this problem is the dict.get function. Another, even more powerful solution would be to use Defaultdict from the Collections module. Let's first look at the dict.get function. This allows us to provide a default value, which will be returned if a requested key cannot be found. So if a member possesses a trait, its value will be retrieved from the self.traits dictionary and returned. If a key cannot be found, the default value, so false, will be returned. Another way to implement this exhibits trait function is with the Defaultdict class. The Defaultdict class is a subclass of the general dictionary type in Python. It behaves like a normal dictionary in most cases, but has one important difference, namely that it accepts a callable in its constructor whose return value will be used if a requested key cannot be found. So accessing a missing key creates that key and initializes it using the default factory. The basic usage is quite easy. We import the Defaultdict class from the collections module and instantiate it by providing a default factory. The default factory must be some callable which returns a value. This returned value will be used if a requested key cannot be found. Our goal for the exhibit trait function is to return false as a default value. That means that if a requested key cannot be found, the Defaultdict should create an entry for that key with the default value false. How about providing false as the default factory when initializing the dictionary? Take a moment to think about why this is wrong. We cannot provide false as the default factory because the Defaultdict class requires a callable as an argument. The Boolean false is not a callable, but a Boolean. So instead, we have to define a function that returns false when called without arguments. Such a function can be seen here. It simply returns false when being called. We can now create our Defaultdict, providing it with the return false function as the default factory. Alternatively to this return false function, we could also use a lambda expression. This would result in the same behavior. However, since we are not discussing lambda functions today, I will stick to normal functions for now. So what is so great about a Defaultdict? The current behavior is still very boring and we could just use the dict.get function instead. The power of the Defaultdict class arises from the fact that it can be provided with any kind of callable. This has several important use cases. One common problem that can be solved with the Defaultdict is grouping items in a collection. Let's say we have a list of some of the pets Castle Kilmere's pupils are allowed to bring to school. We want to group the pets by type, that is having all the owls together, or the cats, and so on. This can be achieved by providing the callable list as an argument to the Defaultdict. We create our Defaultdict using list as a default factory. We then loop through our list of pets. Our first item in the list is cotton, that's Luke's owl. When we try to find this key, so the owl key in the at the moment empty dictionary, it won't be found. Since we use list as a default factory, a new empty list will be created and inserted into this dictionary for the key owl. We then append the name, which is cotton, to the list. The next time we loop through the list and get to the key owl, it will already be contained in the dictionary with a list, and the next name can be appended to this existing list. So what do you think the output will be when looping through this resulting dictionary? Okay, so I hope this is what you expected. We get a list of all the owls, a list of all the cats, and so on. There are more use cases for Defaultdicts out there. For example, we could use it to count the number of pets of each type. So maybe you want to use this as an exercise for after the presentation. How or which default factory could we use to count the number of pets of each type in our list? Let's sum up what we learned. We started out with a common problem that often occurs when working with dictionaries, namely accessing and modifying keys in the dictionary that don't exist. We learned that this can be solved using the collections.defaultdict class. A Defaultdict behaves nearly identical to a regular Python dictionary with a subtle but important difference, namely that it accepts a callable in its constructor, whose return value will be used if a requested key cannot be found. This can be useful in several situations, for example, when grouping objects. Let's continue our journey with a concept probably most of you have heard of, decorators. Decorators are an advanced concept which can be a bit difficult to understand in the beginning, so don't worry if you don't immediately understand how they work. The more you will use and read about them, the clearer the concept will become. So what is a decorator? In simple terms, a decorator is a callable that takes a callable as an input and returns a callable. What's a callable? Typically, when we are talking about callables, we mean functions. So for simplicity, I will stick to functions from now on, but you could equally decorate any other callable, for example, a callable class. Decorators allow us to extend and/or modify the behavior of the callable that they take as an input. And they do that without permanently modifying this input function or class itself. The behaviors changed only when it's decorated. This sounds quite abstract, so let's take a look at some code. The simplest decorator would be one that returns its input function. So right now, this decorator is not doing anything. It receives a function and returns it without modifying its behavior in any way. We can apply a decorator to a function by wrapping it. Given our simple decorator, so the one that is just returning the given function, we can apply it to the sayHello function by providing sayHello as an input and assigning that result to the sayHello variable again. This way of applying a decorator is cumbersome. As you can see here, we had to type sayHello 3 times, once to define the function used as an input and to assign it to the variable again. The more common way of applying decorators is to use the @decorator syntax, which is simply syntactic sugar that prevents having to write sayHello multiple times. So we could achieve the same behavior as before by sticking this decorator on top of our sayHello function. Right now, our decorator only returns its input function, so the behavior of the sayHello function isn't changed at all. This is, of course, not particularly useful. So let's take a look at how we can extend or modify the behavior of the wrapped function. When we want to modify the behavior of the wrapped function, our decorator must be a little more complex. Specifically, the decorator must define a new function called the wrapper function. This new wrapper function is then used to wrap the input function and modify its behavior. An example might look as follows. Let's go through this code step by step. We have our decorator function, which is called goodbye. It accepts a function as an input argument and internally defines a wrapper function. This wrapper function calls the given input function and saves the result in a variable. It then appends the string goodbye, have a good day to the original output and returns this new output. The goodbye decorator then returns the wrapper function. When applying this new decorator to our sayHello function, our output should have changed. Can you guess how it looks like now? Well, the output is hopefully what we or you expected. When our sayHello function is decorated with the goodbye decorator, its output changes to hey there, which is the original output. And after that, goodbye, have a good day, which is the output added by the wrapper function. But what if we want to decorate a function that has input arguments? Since we, of course, want to be able to decorate all kinds of functions, not only those that don't take any input arguments. For example, we might have a function that allows a person to talk to another person, such that Lizzie could say hello to Luke. So how can we decorate this function? We somewhat need to make sure that our goodbye wrapper function can process the arguments, person, and words. This is not that hard. We simply use args and quarks to collect all positional and keyword arguments and forward them to the original input function. Our new code looks similar to the previous version. The only difference is that the wrapper function now collects all positional arguments in the args variable and all keyword arguments in the quarks variable. These are then forwarded to the input function. The rest of the code stayed the same. So take a guess at how the output of the new print statement will look like. Okay, great. This is awesome. We can now decorate functions with arbitrary input arguments, like in this case, strings with Lizzie and Hey Look. We won't dig deeper into the topic of decorators today. There is so much more to discover, and it would be a whole different talk to go into the magic that can be done with decorators. So as a last piece of information regarding decorators, I want to ask you the question why decorators are called decorators. This will be a nice memory hook if you can't remember what they are doing. So think about that for a moment. Why are decorators called decorators? We call them decorators because they decorate other functions and allow us to run code before and after the wrap function is executed, without permanently modifying its behavior. This closes our section on decorators. As a quick summary, we learned that decorators allow us to modify the behavior of a function. We also learned that the decorated function only changes its behavior when it's decorated. This can be very useful. For example, you could implement a decorator that determines how much time it takes for a function to run. We could then use this decorator during development to time various parts of our codebase and then remove the decorator again once all the optimization is done. And last, we learned that decorators are a complex topic and that we have only scratched the surface. Okay, so in the last 40 minutes, we have created several classes and methods. We have a parent class called Castle Kilmere member and several child classes like professor or pupil. As we learned in the beginning, the child classes inherit all methods from the parent class. But there are other, more advanced applications where simple inheritance is not sufficient. This is where abstract base classes come into play. Abstract base classes are useful if your application involves a hierarchy of classes. In particular, in this hierarchy, it should be impossible to instantiate the base class. All subclasses should have a common base class, and all subclasses should implement certain methods defined in the base class. Before jumping to further explanations, let's look at an example. In our magical universe, lots of different types of spells exist. For example, a spell can be a charm or a curse. This makes the spell class a great application for Python's ABC module. To use an abstract base class, we first import Python's ABC module and let our new class, in our case spell, inherit from the ABC class. And then we flag the methods that must be implemented by all the subclasses with the decorator at abstract method. A spell should have a name, an incantation, and a certain effect. Also, each spell subclass will have a defining feature and a cast method. Notice that these are abstract and not concrete implementations. Our abstract base class spell specifies the requirements of being a spell, but it doesn't tell you how to be a spell. We can introspect an ABC to find out what abstract methods it requires using the done-the-abstract methods property. This is especially helpful if the ABC you're working with is not your own. Let's test whether we can instantiate the base class spell using a simple spell, Stuporus Razziato. For this, we call our spell class with a name, an incantation, and an effect. Okay, this doesn't work. Which is exactly what we want actually, since for abstract base classes, it should not be possible to instantiate the base class. So this is what we expected and what we want. Okay, let's create a subclass. The charm class might look as follows. It inherits from our abstract base class spell, and naturally there are easy charms and very advanced ones, so we will add two new attributes, one being the difficulty of the spell, and the other being min year, which specifies at what year students will be able to cast the charm in question. We further implement we add an implementation for the abstract method cast. Let's try to instantiate this charm class, again using Stuporus Razziato as an example. So we saw that we cannot instantiate our base class spell, which is what we wanted. So now we are trying to instantiate our subclass charm. For this, we call the subclass charm with the name, incantation, and so on. But wait, can we instantiate the class with its current implementation? So with this implementation, does that work? No, it does not work. It raises an error at instantiation time. But why is this the case? Because we forgot to implement the defining feature method. And this highlights a big advantage of using abstract base classes. Let's say we have a subclass that does not implement all the methods required by the base class. When not using abstract base classes, we notice this by getting an error quite late, namely only when calling the missing method. With abstract base classes, we get an error already at instantiation time. So a proper implementation of the charm class would look as follows. In this implementation, we have implemented both abstract methods, the defining feature method and the cast method. The rest stayed the same compared to the previous implementation. We should now be able to instantiate the instantiate the charm class, which you can see here. It works just as expected. Note that ABCs only check for the presence of methods, not if they are properly implemented. So in this charm class, we could have implemented the two required methods by just putting pass in the body and no logic at all. So when you notice that you're not implementing abstract methods properly in several of your child classes, this is a sign that the method should maybe not be an abstract method. You might notice another new thing in the code of Spell, namely that we stacked two decorators, in this case, the property decorator and the abstract method decorator. When stacking decorators, it's important to know that they are applied from bottom to top. So how do you think we could express these two stack decorators in the wrapping syntax? Stacking decorators, or these two decorators now in particular, is equivalent to first calling abstract method on the defining feature and then putting that result into the property function. So, but now in which place should add abstract method go when combining it with these other decorators? According to the Python docs, abstract method, when used in combination with other methods, should be applied as the innermost decorator. So keep that in mind when stacking multiple decorators. Let's summarize what we have learned. ABCs allow us to formalize the relationship between a parent class and a subclass. They serve three purposes. First, they let a parent class communicate that subclasses should have a certain structure. Second, they allow classes to identify themselves as having the required structure, that is, meeting the demanded requirements. Third, they enforce that a subclass meet the requirements, otherwise throwing an exception at instantiation time. Lastly, I want to mention that ABCs, similar to decorators, are a huge topic and that we have only seen a small part of it. Nevertheless, I hope that you now have an idea of how they work and why they can be useful. Okay, going on to the next section, where we will take a look at nametuples. Before looking at nametuples, we should review what a tuple is. In Python, a tuple is a simple data structure that can be used for grouping arbitrary objects. Important to know is that tuples are immutable. That means that once a tuple has been created, it cannot be changed anymore. We already use tuples in our magical universe. For example, we defined the pet attribute of the pupil class to be a tuple. Each tuple has two fields, the name of a pet and its type. Ramses, Lily's cat, would be an example of such a pet. Each field of this tuple can be accessed using its integer index. For example, we could get the name of Lizzie's pet by looking at the value at index 0. I already mentioned that tuples are immutable. So once we create a tuple, like Lizzie's pet, we cannot change it anymore. And we can see this in the example on the slide. When trying to change the name of Lizzie's pet to Twiggles, we get a type error that tells us that we cannot assign new values to the items of a tuple. So what are nametuples? As their name suggests, nametuples are a variation, or rather an extension of plain tuples. In particular, nametuples allow us to name the fields of the tuple. This makes it much easier to access the individual fields. Also, it makes our code more readable. In the plain tuple example we've seen above, we could access the values stored in the tuple only by using integer indices, like Lizzie's pet at position 0. When having only 2 fields, this is not too bad, but with more than 3 fields, things become messy. So how can we create a nametuple? This is easy. Easy. There are two kinds of nametuples we can use: collections.nametuple, you can see already, or typing.nametuple. Due to a lack of time, we will only look at typing.nametuple today. Typing.nametuple uses an easy syntax and allows us to specify the type of each field. Nametuples also make it easy to add methods to the class. An implementation of the pet class as a nametuple would look as follows. Our fields stay the same as before. Each pet has a name, which is a string, and type, which is also string. Another advantage of the nametuple classes is that they come with an implementation of the dunder wrapper method. So we don't have to create that ourselves anymore, but we can get a nice string representation of our objects right away, as you can see here, when we print Lizzie's pet. We can access the fields of the nametuple using either field names or their indices. So this is especially useful when having many fields because we don't have to remember the indices anymore. Accessing fields using their field name, like Lizzie's pet.name, also makes our code more readable. Let's think about our magical universe. We don't want our pupils, professors, or ghosts to be immutable. For example, the pet of a pupil might change. A suitable group of people for an immutable class are the Dark Army members. Why the Dark Army members? Because once you become a member of the Dark Army, there's no way back. Each Dark Army member will have a name, a string, and a birth year, which should be an integer, not a string. Sorry for that mistake. We can further specify Master Odon, the leader of the Dark Army, as a class method. We can, with this nametuple class, easily create members of the Dark Army. For example, we can create Karis Fulford, one of the dreaded members, and access the leader of the Dark Army using the instance of Karis. So we get a nice string representation of the Karis instance, and we can access the leader of the Dark Army using the Karis instance. We can further make sure that we cannot change the fields of the nametuple class that we created. That you can see here, where we try to change the name of the Karis instance and we get an error. Let's recap what we learned in this section. Nametuples are an extension of plain tuples that represent a shortcut for creating immutable classes. But they are not the only way to create an immutable class. With Python 3.7, we can also use data classes for this. For those of you who don't know data classes yet, don't worry, they're up next. Okay, everyone, we're almost done. Last up are data classes. According to the PEP on data classes, they are basically mutable named tuples with defaults. We already looked at named tuples and used them for our Dark Army member class. Similar to named tuples, data classes make it much easier to create a class because they implement several useful methods by default. Let's create a data class and see what functionality it includes out of the box. We will use data classes to specify the different departments of Kilmere. We can create a data class by using the @DataClass decorator. Each department will have a name, a head, which is a professor, and a year it was founded in, and an associated ghost. We can create an instance of the department class just as before. So for example, the law department is led by Birdie Brittle. It was founded in 785, and it is hunted by the Mocking Knight. When defining the department class as a data class, Python automatically adds several special methods to the class. For example, the class includes a dunder init method under the hood that looks like this. This is pretty nice. All we had to do is list the attributes of our department class, as done here, and then the Python took care of the rest. So this dunder init method was created automatically under the hood. Dunder init is actually not the only special method added to the class automatically. For example, Python also added a dunder wrapper method to the department class. So when printing the law department instance, we get a nice representation right away. By automatically adding these dunder methods, data classes release us from the burden of having to define them ourselves. We could, of course, still override the default implementation if needed, but most of the time that won't be the case. We can easily add default values to the fields of our department data class. For example, we could add a default value for the field founded in. Although data classes typically mostly store values, a data class is still a regular class, so we can freely add methods to our department data class. If you remember the datetime library from our toString conversion section, then we could use it here to calculate the current age of a department in years. So far, we have used the addData class decorator without any parameters. This corresponds to using the default values of the parameters. We can, however, provide parameters when creating a new data class. Lots of parameters available, so we will only look at a few of them. For example, there are the init and wrapper parameters, which are true by default. When setting them to false, no dunder init or dunder wrapper methods would be created automatically. Another interesting attribute is frozen. If setting frozen to true, its default value is false. Fields are frozen, so assigning to fields will raise an exception. That should sound familiar. Remember that I mentioned in the summary of the Namedtuples that we can use data classes for creating immutable classes. That's exactly what this is doing. Here you can see the Nametuple definition of the Dark Army class from earlier. And when turning this into a data class, we can keep all the code. We just have to add the addData class decorator. And I think this is pretty simple. We just added the addData class decorator and set frozen to true. So let's test that this new Dark Army member data class gives the desired result. As before, we can create instances of the Dark Army member class, like Harris Fulford, and we can access the member of the Dark Army, the leader of the Dark Army, Master Odon, using our method leader. And most importantly, we cannot change the fields once a member of the class has been created. For example, when trying to change the name of an instance, we get an exception, similar to our Nametuple example. Let's sum up what we learned. Data classes are a great tool for creating classes that store a lot of state in the form of attributes rather than methods. Data classes automatically create many useful methods for us, such that we don't have to write them ourselves. We learned that data classes can be configured during creation by providing parameters to the addData class decorator. One example for this is the frozen attribute, which allows us to create immutable data classes. If you want to know more about data classes, consider looking at PEP 557, which introduced data classes, or watch one of the many PyCon talks on this topic. We are now at the end of this talk. The topics we have discussed today are only a small portion of the features and topics that can be worked on using the universe of Castle Kilmere. You will find even more cool applications on my blog or in the GitHub repo of the project. And I'm also planning on extending the universe, so there's more to come. Most importantly, I want you to remember that learning becomes much easier and way more fun if you find a topic you're passionate about and use it for learning. Even if you're not into magic, which I doubt, I'm sure that you will find an equally cool topic to explore the world of Python. So thanks a lot for listening. I hope you enjoyed our journey through the magical world of Castle Kilmere, and I'm excited to hear your questions.